Dr. Abraham, please, can you hear? Are you still with us? We can barely hear you. Okay, maybe we'll come back for that. Let's welcome the coordinator.
Yeah. Kufre, can you hear me? Hello? Can you hear me, Kufre?
Yes, we can hear you. Please go ahead. Okay, well,
Dr. Abraham.
Okay. Hello, sir. Can you hear me?
I said we can hear you. Please, can you go ahead?
Yeah. Good morning, all. So this virtual technical meeting of Calabar NAPE chapter. Wherever you are joining us from, you are well. We wish to remind all of us to be safety conscious wherever you are. Safety, simply is a protection from incident or accident. Find out first thing, something can go wrong. And if anything goes wrong, where will you take as your exit? So find out your exit in case anything happens, because anything can go wrong. If it is a new environment, you need to be acquainted with the environment. If it is your usual environment, then take care of yourself and those around you. We wish all those joining this session from around the world to be very safe. Please stay safe and you are welcome. Thank you.
Thank you for that safety tips. Please, let's welcome the coordinator for his opening remarks. Thank you. While we're waiting for the coordinator, I don't know if Dr. Kufre can proceed with the announcements. Dr. Kufre, please, can we have the announcement now? Dr. Kufre, please, can we have the announcement now? Okay, thank you. It's coming up.
Okay, good morning, everyone. This is the time for announcement. Today, we have the Calabar technical meeting that is currently ongoing. When it is time, the presenter will be duly introduced for him to make his presentation. Then on the 27th of April, 2023, we will have the technical meeting in Abuja chapter. And that will be, the presentation will be done by Professor Charles Ofebu, who is the Director of Geoscience and Earth Resources in Kefi, Nigeria. Currently, NAPE is calling for abstract submissions for the upcoming conference that is holding in June. The theme of the conference is, the conference is holding in November. The theme of the conference is repositioning the oil and gas industry for future energy dynamics. I think we should take note of the deadlines. The deadline for abstract submission is July 31, 2023. Letters will be given out on the 31st of August, 2023, while full papers are expected to be sent on or before 30th September, 2023, while we get set for the conference. The conference will hold from the 12th to 16th of November, 2023. Please, all members are encouraged to pay up the membership dues. Students are to pay 2,000, active members 12,000, corporate bodies 50,000. Please, the membership dues is very important as it will help the association to operate smoothly, because the association depends to a great extent on dues to carry out most of its operations. So we should pay our dues through the account number that is shared on the screen. Check the screen, you will see the NAPE account number. The bank is UBA. The number is there displayed, 100515866 UBA. The bank name is, the account name in Abuja as we speak. And I think our president is speaking in that summit. The theme of the summit is Global Perspective for a Sustainable Energy Summit. It is currently ongoing and will end on the 20th of April, which is tomorrow. We should also get set for the NOG Energy Week 2023, which is commencing on the 9th of July through the 13th of July 2023. The 2023 NAPE Annual International Conference and Exhibition we hold, as I earlier announced when I was announcing the call for abstracts. The venue for the conference is Eco Hotel and Suites at Victoria Island, Lagos. Other details are as contained in the flyer. For our monthly technical meeting, there are sponsorship opportunities. The 2023 Technical Business Monthly Meeting sponsorship opportunities now exist. So you can partner with NAPE to host a technical meeting in one of the monthly technical business meetings of 2023 and showcase your company's technical strengths and edge. Leverage the NAPE platform to reach our diverse membership across the world. Please, for further inquiries, you check the details on the screen. We are also told of the NAPE HMO scheme, which is available for us to access. Please, the details are there displayed on the screen. For further inquiries, the numbers are there displayed, so you can call to find out any information you may wish to have. Thank you very much for listening.
Okay, so
Doc, thank you very much for the announcement. Please, let's welcome our coordinator. Thank you.
Yeah, good morning, everyone. For making it to the first technical meeting this year, I want to especially thank the president of NAPE for the opportunity. I also want to thank the immediate past coordinator, Dr. Ikarapan, for being here today with us, and other members of the ESCO. I can see Dean, Prince Will, and many others that have made it to this meeting. I also want to thank our speaker for today, Mr. Juan Paras, who is speaking to us from Venezuela, and his colleagues, Raluca, Rika, Roman, Requip. You're welcome to this global platform. I want to especially thank the members of ESCO, Uyo Calabar chapter, who are on board as well, the moderator, and every other person. You see, one of the visions of NAPE is to spread knowledge. And we're using this platform to spread knowledge and to tell people about what we're doing as petroleum geologists around the world. And I'm so gladdened that we're able to make this out today. So I want everyone, without much ado, to please sit tight, don't log out while you receive as much information as you can during this technical session. I can also see the coordinator of Warri chapter, Dr. Wilson. You're welcome on board. Thank you very much for this opportunity. Please, we may not have the time to do all the recognitions now. If I've missed you, please bear with me because we need to go straight into the presentation. Thank you very much, and God bless everyone. Okay, so at this time, I would like to introduce the chairman of today's technical session, the immediate past coordinator of NAPE, and a very senior geoscientist, Dr. Ekarapan, to take over from here. Dr. Ekara, please.
Good morning, everyone. I believe I am heard from my corner here. I thank everyone for connecting to this call. I'm so glad that this is a chapter that has survived and has stood the test of time. And we are very glad that we still have professionals connecting to this call. With this kind of rich presentation, having looked at the abstract from the presenter, Dr. Joan Torres, and I know we are going to gain richly from this presentation. I also look at the attendees that are connecting to this call. I see good erudite members of NAPE. I believe, having looked at the attendees connecting to this call, that the president of NAPE and the president-elect of NAPE would soon join us in no time. I'll be putting a call to them while the presentation is on. But for now, we have seen that connecting to the call, we have about 42 attendees. It's a very good representation. The whole world is connecting. And I wish everyone happy listening to this technical discourse. If you have questions, observations, please. If we are not enabled, you are not enabled by, you are being muted, you can chat. And then I will use that to address the speaker to attend to your need. So happy listening and remain blessed. My name is Ekerapan. Thank you. So at this point, I think I will introduce the speaker for the day to take the floor. Or do we have somebody to reach his profile? Hello? Hello, my coordinator.
You don't have it? Okay. All right, at this moment, I'll invite the moderator to read his profile shortly. I'll open the profile. Yeah, that was a miss.
Thank you very much. Juan Carlos Porras is a geological engineer with a Bachelor's of Science degree from the University of Oklahoma, US in 1985, a Master of Science degree in geology, majoring in petrophysics from the Colorado School of Mining in 1992, and a specialization in petrophysics and subsurface data integration from Amoco in Tosca Technology Center from August 1994 to August 1995. Mr. Porras started in the Venezuela oil and gas industry in 1985, working as a well site geologist and log analyst in 1989. He was transferred to the Petroleum Management Department to work as operations petrophysicist until August 1990, when he obtained a scholarship to pursue his master's degree, which he achieved in July 1992. Upon his return, he continued working in the Petrophysics Management Department, and in August 1994, he was assigned to Amoco's Tesla Technological Center to specialize in petrophysics and subsurface data integration until August 1995. After his return to PDVSA, he started working as main petrophysicist in different projects. He worked in PVDSA up until 2020, obtaining a position as a petrophysics advisor for PDVSA's Reservoir Integrated Studies, having as many activities, coordinating of projects and application of new technologies and best practices in reservoir and petrophysical characterization. He was a member of the main committee of PDVSA's Petrophysics Knowledge Community from 1998 to 2002, and a co-founder of 1 minute, please. Okay. Okay. Since 2023, Mr. Porras is a co-founder and member of the board of directors of Interrock CA, working as consultants from different companies in different countries. Okay, so that is a brief profile for Mr. Porras. I would invite him for his speech now. Thank you very much.
Okay, thank you very much for the introduction, and I will share the screen. Please let me know if you can see it okay. somebody that can tell me if the screen is okay?
Yeah, the screen is okay.
Okay, good.
Can you put it in slide view?
Yes,
Presentation?
that was the next step. Is it okay now? Presentation type?
Perfect. It's okay.
Okay, good. Well, I'm gonna start then. First of all, I would like to thank NAPE for this opportunity. I feel really, really excited about it, and having this opportunity to connect with you from the other side of the world, basically. And especially, I would like to thank all those who made possible to have this presentation for you. So thank you very much to all of you. This presentation, I've been doing it in several countries, several places, and I slightly changed it, for the different audiences. The first time I did, well, as you mentioned, I'm now in Venezuela at this moment, but I've been living for a little more than the past 5 years in Argentina. When I first made this presentation in Argentina, most of the audience, probably all of the audience, were geologists. So I have to adapt some things, for them. But this time, I suppose, that being from NAPE, most of you are engineers. So many of the concepts that we're going to slightly review in this presentation are known by you. So we'll just go, through them very briefly to set up what we really want to talk about, which is the rock typing methodology. So I will present some of how this methodology have evolved in time, and the different approaches that we can use for different type of reservoirs. And then I will finish the presentation with some case studies, real case studies that from projects that we have worked in the past, just a few of them, to show the application of this methodology. The content of the presentation, as I said, we'll go very briefly through some capillary pressure concepts. Then we'll go into the core of the presentation, which is rock typing, or the methodology of rock typing, how it was developed. We'll go into the relationship between rock types and water saturation, not very deep. And then a little bit about flow units, and at the end, as I said, some case studies. And then to start with, let's do it with some capillary pressure concepts very briefly, as I suppose you guys handle and manage this concept very well. I myself, as the doctor said, I'm not an engineer. I am a geologist. But with the end, you start working with data and integrated, through the years, you start integrating data that come from different disciplines, that's geology, engineering, and geomechanics, and so on. Well, basically, and we need to say this, we need to set this up because this is the base for the development of the rock typing methodology. Capillary pressure is basically the difference. Just a second, I need to move this screen. It's basically the difference in pressure between a wetting phase and a non-wetting phase in the reservoir or in the lab. And there is this equation that is not new. It comes from 1921 by this guy called Washburn, that relates capillary pressure to R through interfacial tension and contact angle. This R is related in the lab to the radius of the capillary tubes that are used. But in the reservoir, we can relate it to the pore through radius that controls the flow of the fluid in the reservoir. In the lab, sigma will be the interfacial tension for mercury. In the reservoir, it would depend on the type of fluids that coexist in the reservoir. And then again, in the lab, sigma will be theta, sorry, will be the contact angle for mercury. But again, in the reservoir, it will depend on the fluids that are present, coexisting in the reservoir. As you see, there is a difference between the non-wetting and the wetting phase as the concept of capillary pressure. But capillary pressure has like two, let's call it like two different areas, or one that is the pore throw control that comes from the previous equation. Let's call it the Washburn equation, where PC, or capillary pressure, is equal to 2 sigma cosine of the theta, cosine of theta divided by R. But there is also a height control that relates capillary pressure to height, and height will be the height of the hydrocarbon column through the difference between the specific gravities of the fluids that coexist in the reservoir and the gravitational constant G. So we see the capillary pressure, we have like the pore throw control related to pore quality or rock quality, but also to height. In this case, height of the hydrocarbon column, which is the same to say as height above the free water level in the reservoir. Okay, which is the point or the depth where, you know, the level where capillary pressure is equal to 0. So this is something that we have. So this is taken from this paper from Snyder. Basically, we have a wetting phase, right? Most of the times this is water. And this wetting phase elevates above the free surface by capillary pressure forces, or by capillary forces, until the adhesive and gravitational forces are in equilibrium, which will be this point here. Capillary pressure will be the difference in pressure measured through the interface in the capillary, as we said, the difference between the pressure of the non-wetting phase and the wetting phase. And in the reservoir, basically this pressure results from the difference in pressure gradients produced by the density difference between the non-wetting phase and the wetting phase. Use oil and water, you know, to make a simple example. We need to talk about wettability very briefly. You know, how do we measure? Not we measure, because we use lab techniques, usually the Amot technique, to measure wettability in the lab. Basically, when we have a water-wet rock, where the contact angle of the wetting phase, in this case water, will be less than 90 degrees, usually close to 30 degrees. When we have an oil-wet phase, or when water is acting as an oil-wet phase, the contact angle will be greater than 90 degrees. This is just an example. I mean, it doesn't have to be 150, it can be 140, but it's greater than 90 degrees for an oil-wet system. For rock typing, the capillary pressure data that is used, or that should be used, is a mercury injection capillary pressure. And there are some reasons for that. This is a capillary pressure. This was drawn by hand, just to show some points in the capillary pressure profile, or the capillary pressure curve, that are going to help us determine with a very quick view what the quality of the rock represented by this curve is. And these points, sometimes one of them is the entry pressure, which is the pressure where mercury starts, you know, entering the rock sample in the lab. Then we have the displacement pressure, which is the pressure at a non-wetting fluid saturation of 10%, or we can say mercury saturation 10%, and then we go to with that value of 10%, we can go to the capillary pressure curve and measure the displacement pressure. And another important point through the capillary pressure curve is the threshold pressure, but it's very subjective, because, you know, it's the point where supposedly we start the path of the mercury going into the rock. But, you know, we can argue that this point is not exactly where put it for this presentation, but it might be here, or it might be a little bit to the left. So sometimes for normalization, it's better to use, when we're talking about different capillary pressure curve, it's better to use the displacement pressure for comparison because it is normalized or is set for 10% water saturation. Then we have the so-called horizontal or pseudo-horizontal curve, which is the plane part of the curve that is going to tell you, how good the rock is in terms of fluid capacity, how much mercury is the rock receiving in the test. If this horizontal part is longer, it means that we have a very low increase in capillary pressure for a lot of mercury being intruded. So it means that the rock is has very well connected pore system, rock quality in terms of fluid flow capacity. Remember I will have to say, when I'm talking here about rock quality, I'm talking about flow capacity, okay, and flow efficiency of the rock, not necessarily higher permeability or higher porosity, but a higher flow capacity, which is related not to these properties separately, but to the relation between them. That's to say, to the K-feed ratios, which will be later on. Then in the capillary pressure, we see that we have this part that we start moving up. You see that we have a higher increase in pressure for mercury intrusion, which means that we are entering the part of the rock that has porous quality, poorest interconnected pores, until we get to the so-called minimum water saturation point right here, which is, I call it minimum water saturation. Sometimes we call it the irreducible water saturation, but I think that's not the right way to call it, because it depends on the height that we're talking about in the hydrocarbon column. Remember, there is a relation between capillary pressure and height. So if the height of the reservoir corresponds to a capillary pressure of 100 psi, then our minimum water saturation or irreducible water saturation will be here, even though we haven't found the minimum water saturation if we had a bigger or thicker hydrocarbon column. If we're talking about a hydrocarbon column whose height corresponds to a capillary pressure of this is 7,000 psi, then that's okay to say that this will be my irreducible water saturation. But that's why I prefer to call this point here minimum water saturation. And then when we relate this to height above field water level, we can start talking about irreducible water saturation. The advantages of mercury injection curve is that we can get our mercury injection capillary pressure data. We can get fast results. We can go to the highest capillary pressures, which is not the case for centrifuge or for a porous plate. We can work with a wide range of pressures. We have reasonably accurate results. We can work, or we can do the test, the mercury injection test, in plugs, using a conventional porosimeter, but also we can conduct high pressure mercury injection test on rock fragments. So even in cuttings, we can do this test. So this is a big advantage that we cannot have with other methods. We can derive values of a specific surface and the distribution of pore diameters, which is related to rock typing. We can have drainage imbibition curve in the system. And also, this is very important. We can get the minimum water saturation, as we saw in the previous slide, which is related to the height above the free water level. Remember, free water level is the point where the capillary pressure is equal to 0. Some disadvantages, yes, it's a destructive test, it's polluting mercury. And when we do the conversions to reservoir, or when we want, let's say it this way, when we want to calculate height above free water level, we require conversion to reservoir fluid system, which is very easily anyway. So it's not really a disadvantage. It's something, it's just an additional step that we need to do before we calculate this height above free water level. Okay, mercury injection. To sum up, we can obtain reservoir rock quality, reservoir thickness. In fact, recently, a couple of months ago, we finished a work when we used only pore throat radius curve coming from mercury injection capillary pressure curves to determine pay versus non-pay in the reservoirs. And the results were very, very, very good. We can obtain fluid saturations, fluid contact, seal capacity of the rock. That is, what is the pressure that the seal rock can support before it breaks. We can also look easily the thickness of the transition zone related to the rock type. Remember, we have different rock types in the same reservoir. But for this talk, we're gonna be covering rock typing, which is directly related to reservoir rock quality. Here are some examples of capillary pressure curves. In this line here, we have conventional pressure capillary pressure curve, up to a little less than 2000 psi. And then we have, for the same reservoir, in the bottom, we have high pressure mercury injection capillary pressure curves. So we have to be careful, what data to use. Lately, or from some years, starting some years before, usually most, not to say all, the measurements are made at high pressure, but sometimes we don't need the high pressure measurements to conduct a rock typing or to do an analysis of rock quality in the reservoir. Remember that the high pressure, in this case, almost up to 70,000 psi. But do we need that high pressure? It depends, as I said before, on the thickness of the hydrocarbon column. If we have a small thickness about the free water level up to the closure point, probably we do not need to use high pressure mercury injection curve. And we can see the difference. I mean, there is a difference in the result. When we cut all these graphs at a mercury saturation of 20%, I use 20% just for example. I could have used another number, but see what happens. In this row, in the upper row, we have, for the same, this here that is in green it comes from the same reservoir as this. The blues come from the same reservoir and the oranges come from the same reservoir. So when we cut water saturation, mercury saturation at 20%, for a conventional capillary pressure curve, we have a range of 100, approximately, from 100 to 1000 psi. But in the high pressure mercury injection, we have a range of 80 to more than 1000 psi. In the case of the blue reservoir, we have a range for the conventional pressure between 70 and 200, a little more than 200 psi. But then look at this difference. For the high mercury injection curve, we have a range of 40 to 1000 psi, which is a big difference. So doing an analysis with the conventional pressures, specifically, especially in this case of the blue reservoir, as compared to high pressure mercury injection curve, is going to make a big difference in the results that we obtain regarding rock typing. Then for the orange reservoir, we see the same thing, and we have at a 20% mercury saturation, a range of capillary pressure between 90 and 600, but for high pressure mercury injection, we have a range between 200 and 3000 psi. So we have to be careful. We need to use the data that best corresponds to the reservoir that we're talking. If we have a reservoir with a small hydrocarbon column, we'll be okay with conventional pressure capillary curve. If we have, very tight reservoirs that have longer transition zones where we have a thick hydrocarbon column above free water level, maybe we need to go to, and that height of the hydrocarbon column surpass or is above the corresponding capillary pressure of a conventional test, we need to go to the high pressure test. But we have to be very careful. It's not that we, since we have high pressure mercury tests, we need to go ahead and use them at first. Here we can see a difference between real data. I know, the sampling might be biased a little bit, but there is usually a difference between conventional pressure and high mercury pressure for the same reservoir, even for the same reservoir. One advantage of this capillary pressure that we can look at the capillary pressure, and I'm sure you know this. We can look at a set of capillary pressure curves, and we can, very quickly, immediately, we can relate it to rock quality. In this case, we have two groups of capillary pressure curve, one group to the right, one group to the left. The group to the right corresponds, the group of capillary pressures to the left corresponds to a pore system that is of very good quality. Okay, you see they have what we can see about this capillary pressure curve. We have a smaller entry pressure, displacement pressure, threshold pressure. Remember, we looked at that. And we have a lower minimum water saturation for the highest capillary pressure curve. For the curve at the right, we have higher entry pressure, threshold pressure, displacement pressure. We have, very short curve. Basically, we do not have a horizontal part of the curve. We have a kind of, diagonal curve and a very high minimum water saturation. And this corresponds to a poor quality pore system. And we can do this immediately just by looking at the capillary pressure curve. We don't need to see porosity. We don't need to see permeability. We don't need to see any other property. Just the shape of the capillary pressure curve is going to tell you the quality of the rock. And what good thing about this, and that's very important also, look here below at the bottom. It's independent of lithology. We had three very similar capillary pressure curve. One corresponds to a dolomite, the other to a feldspathic sandstone, and the third one to a quartz arenite. And then for the poor quality rocks, we have also a different type of lithologies: limestone, sandstone, dolomite, and feldspathic sandstone. So the good thing about the capillary pressure curve is that we can relate it to pore quality or rock quality independent of lithology, because the capillary pressure curve are looking, putting that in quotes, at the pore system, not to the rock system. So we are doing tests that are, determining the quality of the pore system independently of the rock or of the lithology. And that's a very important issue, because if we have a capillary pressure curve of this type of some corresponding lithology in a basin or a reservoir in Nigeria, and we have the same capillary pressure curve in a reservoir here in Venezuela, we can say that independent of lithology, independently that they are one in Nigeria and one in Venezuela, they are of the same rock quality. And that's a very important issue. As we probably already know, we already talked some about this, when we increase the irreducible, I'm calling it irreducible, but as I said, I prefer to call it minimum water saturation. When it moves to the right, we have a decrease in rock quality. When we increase entry pressure and also displacement pressure and threshold pressure, we have a decrease in rock quality. And when we have a set of capillary pressure curves, as we looked at the previous slide, when we move from this corner this way, we have an increase in the K-feed ratio. We can see the values of permeability and porosity, increase in the K-feed ratio, which corresponds to an increase in pore throat radius and, of course, an increase in rock quality. So just by looking at a set of capillary pressure curve that come from different formations. We can say, okay, this curve corresponds to a rock that is of better quality than this. The purple curve corresponds to a rock which is of much better quality than the green curve, to say something, just as an example. Okay, we talked before, and I mentioned before the necessary capillary pressure conversion when we need to calculate height, because there is a direct relation between height and capillary pressure. Height is equal to capillary pressure at reservoir conditions, and depending of the, for this unit, divided by the water gradient, which is 0.433 times the specific gravity of the wetting phase, in this case water, and the non-wetting phase, in this case I'm using hydrocarbon. And to get the capillary pressure at reservoir conditions, it's just a very simple equation where we took the capillary pressure at the lab and multiplied by sigma cosine theta of the reservoir divided by sigma cosine theta at the lab. And these values are known. We know the value of sigma at the reservoir, for a corresponding fluid system. If we have oil and water, the values of sigma and theta are known. And in the lab, if we have mercury and air, which is usually what we really use, not water, we know the values of sigma and theta. So knowing all these values, we can very easily make the conversion from lab to reservoir. And from this, we can calculate height above free water level. Of course, we need to know, it's important to know where the free water level, or at least the oil water contact, is in the reservoir. So let's go now to what we're gonna actually, the core of the talk, which is rock typing. Oh, sorry, I used the Spanish word here, which should be evolution of rock typing. And I'm not sure if I should call it evolution, but it's like, all the changes and different approaches and focuses that have gone through rock typing since many years ago. And we can see that even in 1950, Archie defined petrophysical rock types, okay? Then in 1970s, we usually use K versus phi graphs to determine the quality of the rock. But in 1980, Winland, which is a guy who worked in AMO, developed his famous equation that relates log of R35 to the air permeability and porosity. R35 is the mercury saturation, will be the pore throat that we can obtain from a capillary pressure curve that is related to a 35% mercury saturation in a capillary pressure test. Then in the early 80s, Dr. Lucia in Texas A&M University, I think, he came up with a classification in carbonates using what he called the rock fabric number. In the late 80s and early 90s, I'm not sure if that's the way to pronounce his name. He's a guy from Nigeria. He developed the RQI and FCI methodology to determine rock quality and flow units. In 1992, Pittman came up, he extended Winland's work and came up with relations that not only relate R to permeability and porosity for 35% mercury saturation, but for different mercury saturations. In 2001, this guy, a group of guys, Spirin and some colleagues, they said, well, what happens in Taiga sands? Should we use air permeability? So he proposed an equation to relate R, the same pore throat radius that we can obtain from capillary pressure curve, to porosity, but this time using Klinkenberg permeability and not air permeability, as Winland and Pittman suggested in their work, or used at their work. In 2002, Dr. Roberto Aguilera developed an equation that also relates R35. Remember that R35 is the pore throat radius that corresponds to a capillary pressure, or sorry, to a mercury saturation of 35% that is obtained from a capillary pressure. So he developed this equation, and we're going to see the comparison between Aguilera's equation and Pittman and Winland's equation in some slides later. In 2012, Su and Torres Verdin, I think they are in the University of Texas, they suggested a classification using a bimodal normal density function. This is something, you know, kind of a lot of physics and mathematics involved. So if you need to know more about this, I invite you to read the paper or the dissertation. In 2013, in the University of Calgary, they proposed, I'm going to show the slide later, to extend this classification to non-conventional reservoirs. And many people have worked about this. In Interrock, we have developed recently, I mean, we just finished this work about a month ago, is to be presented in the URTC in June in Denver. We developed a work that was directed by Mr. Rafael Paneso, which is one of my partners in Interrock, an RT index to determine for rock typing classification for non-conventional rocks, for non-conventional reservoirs, I'm sorry. I'm going to show you very briefly about this because it's not it's not published yet. It will be published hopefully in June, you know, two months from today. So this is, you know, how we can say, I mean, is this the evolution of rock type? Well, maybe different approaches of different focus that rock typing have had throughout the years, starting many years ago, you know, like 80 years ago, in 1915, when Archie first defined petrophysical rock types. How this concept of rock types, as we see it now for conventional reservoir, came up? Well, if we look at the permeability, and this is the work that was developed in Amoco, basically by Winland and his colleagues. If we look at a permeability versus porosity plot, maybe we can say, well, we have a more or less a linear solution here, and we can determine a K-field law, which is something that I do not like. Not every reservoir behave with a K-field law. And when we do projects, you know, sometimes the clients, they say, we need to determine the K-field law, but simply there is no K-field law for some type of reservoir. So that shouldn't be an objective necessarily in this type of projects. But these people in Amoco, they are starting to, this is the solution they had before, the K-phi. Remember we said in the 1960s, or in the previous slide, in the 1970s, the K-phi graph or the K-phi law. But where they started to look at samples along this line, I mean, this is a mathematical solution, but not necessarily a geological solution. They started to look at these samples, and they said, sorry, and they found out that the samples, like this sample right here, this right here, this right here, corresponded to different rock types. So why do we need to, through a mathematical relation, connect rock types or rocks or samples that corresponds to different rock types? As I say, no, we need to come up with a different answer for this, and we'll look at this in a few slides up. But let's first define rock types. We have, and this is a definition. This is a definition we came up with after looking at definition from different authors. I mean, and this is come from 1999. It's nothing new. It's a unit of rock with similar petrophysical properties and a consistent relation between porosity, permeability, irreducible water saturation. Maybe I should add for a specific height above the free water level and pore through radius. Rock types represent units with similar flow capacity. Okay. Of course, they are obtained preferably from core data, and also correlation with rocks. And the main classification parameter to obtain the rock type is the pore through radius, which is the connector of the pores in the rock. We might have very big pores, but if we have small pore throats, then the K-Phi ratio, the relation between permeability and porosity, will be very low. The pore through radius will be very low, and the flow capacity of the rock will also be very low. So going back to the work made by Amoco, we have here this K-Phi plot, and they look that these samples, along this K-Phi law that we looked before, had very different properties, and those properties could be seen in the core, in SEM, in thin section, and also the capillary pressure behavior was very different from one sample to the other. If we're going to move down in this cloud of points, I want to see how we can very easily see that the rock quality here is less than the rock quality here. We can also see that in the core, and of course, the capillary pressure behavior is different. We have a third sample, and the fourth sample, very poor quality, very tight, no porosity, no permeability. And see the capillary pressure curves, from sample 1 to sample 4, they move to the right. Entry pressure is higher, threshold pressure, displacement pressure will be higher. So we have a poor quality rock as we move from rock 1 to rock 4. So that's why they come with this, or Winland at this moment, relating porosity, permeability, and capillary pressure curve. Why we say capillary pressure curve? Because he used pore radius determined from capillary pressure curve. If we look at this graph, we see that we have 4 throw lines, and this is the way that they came up with this classification after doing the start. Mathematically, they determined relations in this pore throw model that was developed by Winland in Amoco in the 1980s. He used 82 samples for, we have to say, for conventional reservoirs, but we went for, he went for low permeability to wells with very good permeability, and he generated regression between porosity, permeability, and pore through radius, finding that the best correlation was obtained for the percentile 35% water saturation. And he came up, this, I say here, Pittman 1992, because Winland didn't publish his work. It was an internal work, he didn't publish. It was published by Caloxi in 1980, but this specific information, I took it from Pittman's paper from 1992. Caloxi published Winland's work, and this is Winland's equation that relates R35, which is the pore through radius corresponding to a mercury saturation of 35%, air permeability, non-corrected, and porosity, in this case of this equation, in percentage. So if we look at capillary pressure, what do we mean by R35? If we throw what we call the capillary pressure profile, we see that we can connect dots along this capillary pressure. And we see, for instance, in this case here, we have a small increase in pressure and a very big increase in mercury saturation. In this case right here, we have a small increase in mercury saturation, higher increase in capillary pressure. If we move, and this is the value of mercury saturation, 35%. We move to the capillary pressure curve, then we move to the right. And remember, there is a direct conversion between capillary pressure and R from Washburn equation that says that PC is equal to 2 sigma cosine theta divided by R. So we can directly convert R to capillary pressure, so from capillary pressure. So this value of R, whatever it is, is greater than 10 and corresponds to a megaporous rock, will be the value of R35. That is the value of R, the pore through radius that corresponds to a mercury saturation of 35%. So that's what R35 means. And then we have something like this. Instead of having a K-Phi law like this, we have different curves or different lines that represent different rock types contained in this, between these two lines. Rock type 1 of better quality, rock type 2, rock type 3, 4, and 5. which is the porous quality. They called it mega, macro, meso, micro, and nano, and we'll see which are the divisions of this type of rock. Also, we can relate it to phases, but what can we see here? For instance, phases 1, which is the blue, it would be a very good quality. It would be of regular quality. And the same for our phases. So what can we conclude? That there is no direct relation between rock type as determined from the K-field ratio or from the pore radius to phases, because it depends on the diagenesis processes that these phases has undergone through time. So we can start with a phases which is of a very good quality, initially, very good rock type, but it can go through the diagenetic processes that decrease the quality of the rock for that particular phases. Okay, so this is an indicator of the K-field ratio, is an indicator, or the K-field ratio, indicator of rock flow and storage capacity. Remember, when I talk about rock quality, we are expressing this in terms of flow capacity. Here we have two rock types, rock type 1, rock type 2. We see that they have approximately the same permeability, but rock type 2 have more porosity. Is this a better rock? Well, not necessarily. It has a bigger porosity, but its flow efficiency is lower, because for a very big storage capacity, the flow capacity will be the same as this rock type right here. So if we put it in simple words, here we're going to have a lot of fluid, but we're not going to move as much fluid as there is stored. But in this case, probably we do not have much fluid, but we're going to be able to move most of the fluid. So that's why porosity itself is not an indicator of rock quality in terms of flow efficiency. Remember that. Let's move here. Then Pittman, he developed his model in 1992 with 200 samples with different ages, different rates of porosity and permeability, different type of lithologies. And he came up with these equations. Remember, Pittman had the R35 equation, or sorry, Winland had the R35 equation. Pittman came up with 12 equations, I believe, or 14 equations related to different mercury saturation, because he said, well, why R35? Why isn't the reservoir related to a mercury saturation that is different from R35? And maybe he's correct. So we have now different models for a reservoir. But now we have a problem. We have Pittman's equation, which are very many. We have Winland equation. Which one do we use? Well, there is some methodologies. We use the intrusion plus to determine which is the value of the pore throat that is dominant in a particular sample. This still doesn't give you the model, the Winland or Pittman model. We can use then the apex plots, which are defined in Pittman work, where they can give you a range, right? Depending on the apex of the curve, they will give you a range of the mercury saturation that corresponds to any of the different models. Remember, the models are related to mercury saturation. And then the so-called one-to-one plots, where we plot the values of R for each sample obtained by all the models, which are the previous equations. We plot those against the values of corresponding values of R that come from the lab. And where we obtain a line that is closer to a 45-degree line, maybe we should select that model for that particular reservoir. At the end, we see these are different lines corresponding to different models: R35 Winland, R35 Pittman, R45 Pittman, R40 Pittman. Which is the effect? Well, you see that as we go from R35, let's say Pittman, to R40, these lines move up. So that's to say that if we have some work of good quality here, if we go from R35 Pittman model to R45, we have less rock of good quality, because these lines are moving up as we go from values that are from, as we go to models that are related to higher mercury saturations. So this is the rock type classification they came up with: megaporous, a radius more than 10, macroporous between 2 and 10, meso between 0.5 and 2, micro between 0.1 and 0.5, and nanoporous less than 0.1. And if we want to relate this radius and this rock type to K-field ratio, this will be the approximate relation between them. If we don't have capillary pressure to determine R, which is the radius, we can use K-field ratio with these values to approximately determine the rock types. This is a comparison you can see of K-field values against R. You see the K-field values to this 0.5, 10, 100, and 1000, the dashed black lines, and the colored lines correspond to the different models. So we can see here that the R35 Pitman model is very, corresponds very well to these values of K over phi. We can always move the value of K over phi and maybe use, I don't know, instead of 1000, 2000, or 3000 to exactly match the R35 Pitman model. But see how the relation is with different models. Also, Aguilera came up with this equation. Remember, we talked about this. He used more than 2,500 sample sand and carbonates from a set of data that came from Quantum Pique. He came up with this equation. How they compare R35 Winland to R35 Aguilera? Well, see here. Aguilera will be the dash one, and the colored one will be Winland. So we have to be careful because you see that the limits are a little bit different. But see, we have different focuses, different approaches. For unconsolidated reservoirs, we can use this, but what happens? We have probably all of the rock will be of a good quality. For instance, and this is a real case where we have rock type 1 of very good quality and rock type 2. Those were the only type of rocks present in the reservoir, sorry. So what we need to do is subdivide the good rock quality, maybe in rock type 1A, 1B. In the other case, for tight reservoirs where we have very poor quality, and we know that some of this poor quality rock is reservoir rock, so we need to do the same. Subdivide this rock type 4 in this case, because maybe 4C is a silt rock, but 4B and 4A are still reservoir rock. So we need to do those subdivisions for the ends, consolidated reservoirs as well as tight reservoirs. In naturally fractured reservoir, also we can use some approach. Of course, we know that if the reservoir fractures, we're going to have an enhancement in permeability. But we have points that represent the matrix in the reservoir, the matrix rock type. But then we have something like this, the fissure of fracture samples can give you or can give us relations like this, depending sometimes on the phases, sometimes on by group of porosity. So we need to start doing that. This is a real sample where we could determine different. This will be the.
Hello,
this
John.
will be,
we have
yes?
10 minutes. We have 10 minutes more, please, before questions.
Okay.
10 minutes more.
Okay, and then we want to determine this relation depending on the groups of porosity. In carbonate reservoir, there's also the rock fabric number related, was developed by Lucia, and see he determined 3 classes of rock fabric number. We can see it graphically much better. For limestone as well for dolomite. How do this compare to rock types? Well, from K-phi, something like this. This class 1, class 2, and class 3 are the rock types for Lucia. But see, if we compare this to K-phi ratios, it's something different, so we have to be careful how to apply this. For non-conventional reservoir, we can still do the same. And as I said before, the University of Calgary suggested going to the non-conventional rocks, using the same K-phi ratio. But we know that for the rock typing in non-conventional rock, we need to integrate a lot of data. As I said before, in 2023, this should be, I'm sorry about this, we came up with a RT index, which is a function of TOC, total porosity, proportion of oil gas in the rock, and brittleness. The relation between rock type and water saturation. Here, imagine we have pre-capillary pressure curve. For this capillary pressure curve, at different heights, it means that we're talking about different rock types. But if we have the same rock type or the same rock type at a particular height, it means that we will have different water saturation. So there is a direct relation between rock type and the height above free water level. For the same rock type, the difference in water saturation will depend on the height above free water level. For the same height above free water level, the difference in water saturation will depend on the rock type. Let's pass this. This is an example of rock quality just related to capillarity, where we see that for the poor rock quality, we will have an increase above free water level just by capillarity. To model water saturation, I just want to go very briefly and go directly to the case study. We use usually, the J function that relates the water saturation, capillary pressure, and the quality of the rock. We can have J functions for a group of rock types. We can see that here a 1J function that can work well for a given, for different rock types. But also we can have, for different rock types, we need to determine, if we can determine a differentiation between these, we can come up with different or multiple J functions depending on the rock types. The modified J functions just includes the value of N, which is a cementation exponent, to try to include the tortuosity of the capillary tubes. We looked at this capillary pressure corrections that we need to do before converting to reservoir, are closure correction, clay water correction, stress correction, and wettability. What is the effect? You can see here. This will be the original curve, and the corrected curve will move down and to the right. And that will be for all cases. So the effect of corrections, decreasing porosity, increasing entry pressure and minimum water saturation. In terms of modeling of water saturation, we have a more extended transition zone and increasing the irreducible water saturation, increasing the cementation exponent, decrease in N. That will be the effect of this correction, which means that the impact on the reservoir dimension will be significant if we use this data to determine net pay. This is an example of a comparison between a model water saturation in red and in blue, the water saturation determined from the resistive model. And a second example here. Here we see a difference, and we need to see why, because remember, the model water saturation brings us to regional reservoir condition, and this cannot happen. The regional water saturation cannot be higher than the actual water saturation. So there needs to be a correction in here. So rapidly flow units, continuous stratigraphic interval that maintain geological architecture and rock types. What we pretend to do is going from a petrophysical interpretation from rock types to group these rock types using different tools until we obtain different flow units, which are very more manageable for in a simulator, to say the case. So let's go to some case studies. In this case, see this example, we have these intervals that were produced, that were tested with water produced in 2006. And then in July, they were also tested, also water production. We did the SW modeling, and here we see that these points where the water saturation from both models, J function in this case and resistive model have the same value, corresponds to zones where we are still in reducible water condition. They were tested and they produce 0 water, 100% oil. So this was an example of using all these methodologies to obtain water-free production. Here we have a case where we could subdivide the nanoporous rock and obtain more quantity of reservoir rock, as mentioned before. This is a case of low resistivity pay, where, with resistivity very low, all the water saturation were very high, saturation was modeled, and we could identify some intervals that were tested and produced oil that were bypassed before. And this is an example, doing the water saturation model, where we initially, this was considered as one compartment, and we could determine that, wells A and C, from the water saturation modeling, initially, after doing the rock type, we could determine that wells A and C had a different free water level or water contact or all water contact that wells B, D, and E. This also an example, a case study that was presented in a SPWLA, where we could correlate the rock typing profile to a PLT profile and see the blue curve is the flow unit speed, K over phi, and see we could determine that the flow units determined from rock types had the better flow unit had the most contribution to flow, and then the regular flow unit had a very discrete contribution to flow, and the poor flow units determined from rock typing had a very poor contribution to flow. So this time we could relate the rock typing profile that we can determine to, which is the final goal. How does this relate to production? So we could do that using a PLT. Sometimes we don't have much PLTs to do the calibration or the validation, but this time we could do it, and it worked very well. And lastly, we have this case where we had, you see, this is one block of sand where we have high resistivity, sorry, high resistivity at the top, high resistivity at the bottom, and very low resistivity here. What was the reason? That this part of the reservoir was the best flow unit, best rock quality, and all the water came in through this flow unit. So it's basically this flow unit 8 had a 68% of the total flow capacity, and that's why the water came out through this flow unit. And sometimes we say we cannot have water over oil. Well, we have it in this case, but it's a matter of rock quality. Rock quality B was very poor, rock quality A was very good. So the water came in through this interval A. So, well, at the end, when we do rock typing or any other petrophysical work, we need to integrate, all the information, all the data that come from geosciences, that come from rock analysis, for core log analysis, core log integration, engineering integration, until we get an integrated petrophysical model. So the key here is integration. So, well, I'm sorry I had to speed up at the end, but I want to thank you again for the opportunity. Thanks a lot.
Thanks a lot.
Thank you so very much. Over to you, Chairman, please.
Yeah, thank you a lot. Thanks a lot, Dr. Joan, for this lofty presentation. It's a detailed work, and see a lot of research work and looking at varied samples from varied petroleum basins. And we've learned a great deal on the application in reservoir characterization. You've talked about wetting phase, wetting and non-wetting phase. We've also learned a lot about the pressure interplay in reservoir reducibility. We've also learned greatly, majorly, on the way to go when you have abnormal production zones, maybe tight reservoirs. And we also came up with the model of mercury injection and the different models that mercury injection can be used to handle reservoir producibility. We also see, and what I personally gathered from the study is that there is a difference, the interplay between the pore throats and the pores itself. We could have a large pore and the pore throats can restrict your production. Having gone home to sleep at the pores of the reservoir porosity is high. The portraits could be hindrances. I want to give this floor to anyone who has a question. If you are not enabled to speak, and you can then chat your question or observations through the chat, wherever you are in the world that is connected to this call. I give this floor before I come up with my own observation and possible questions.
Yes. Should I answer? Because yeah, we can have the slides, no problem. I will correct the word that I had in Spanish.
No, at this level, I am throwing the open to the floor to your
okay, I'm sorry.
attendees. Yes, yeah. So I will tell you when to come in if the questions are there. Yeah, as the question comes in, I will read the questions for you and give you the opportunity to take the floor in handling them.
Okay, thank you very much.
Okay. Can I ask directly, or I should send a chat?
Okay, you can ask directly if you have access, please.
Okay, my question is, thank you, Mr. Joan Carlos, for your presentation. My question is there
you introduce yourself, you see where your affiliation. If you have a question, introduce yourself, your affiliations, where you work, and then you go straight to the question, please.
Okay, my name is Dr. Kufre Udo. I teach at the University of Uyu, Department of Geoscience.
That's fine.
And Physics. My question is there a correlation between capillary pressure and pore pressure? Is there any correlation, or is there any relationship between the two? That is my question.
Well,
thank you, sir.
Yeah, actually, I would say there is not a yes or no answer for this. There are two different concepts, the pore pressure and capillary pressure. There might be cases, we haven't really studied the relation, but there might be cases where there is a correlation when we do these conversions to the reservoir, but remember, it will depend. The capillary pressure is directly related to rock quality, right? And the pore pressure has, I would say, an ingredient of the fluid that the pressure of the fluid is certain, at the rock. So there might be a relation, but the concepts are a little bit different.
Okay.
Can I ask a question, please?
Okay, go ahead.
All right. Thank you very much, Dr. Joan. This is a fantastic presentation and of great benefit. I hope that we'll be able to have the slides. Thank you very much. My question is this. I saw some scanning electron microscope images that you presented alongside with some thick sections. How does it help? How can you determine your permeability or capillary pressure or right typing using those SEM messages? Images. So is there any correlation? How do you go about the analysis?
Yeah, that's a very good question, because the SEM information is a qualitative information, and it's not quantitative. So you need to. Is there? I see like an echo. I hear like an echo. Well, see, the SEM is a qualitative information. So sometimes, how do we relate this to? I say sometimes we cannot quantify that, but what can we see in the SEM? For instance, grain size, okay, grain angularity, grain sorting. If sorting is, I don't know if you are familiar with the concept. If we have small grains between the porous space between bigger grains, so that will make a smaller permeability. That will make the permeability to decrease. Also, what type of clay do we have? Something that I didn't present because of the time. So we have different type of clays, and the clays will grow, the orthogenic clays will grow preferentially in the pore or in the pore throat. So if we have, for instance, kaolinite, and we can see that in an SEM, the kaolinite is going to grow more in the pore, and it's not going to affect the pore throat, not much, just a little. But for instance, elite or chlorite are type of clays that are going to plug or to clog the pore throats, and that will decrease the rock quality. So looking at the information from the SEM is very helpful when you relate that to all other type of information to determine rock type, because we can see grain size, grain sorting, angularity, and especially the type of clay that is present in the rock.
Thank you very much.
All right, thank you. Dr. Joan, I have this question that comes from Nigeria here, and it's from Morofedin from Laukote, Abomasho, and he is asking, the question is, what happened at crossover of some of the capillary pressure curves? What happened at crossover of some of the capillary pressure curves? The question comes from Morofedin Adabanjija, Department of Earth Science, Laukote, Abomasho, Nigeria. Please, can you handle this?
Yeah, I didn't get what happens.
So what happened at crossover of some of the capillary pressure curves? What happens? What happened?
Yeah, when there is crossover of the capillary pressure curve, when they cross each other.
Yeah, when they cross each other.
Yeah. When you see, when we look at the capillary pressure curve, of course, for this talk, I presented simple examples, okay, because of the time and all that. But yeah, when the capillary pressure curve start to cross, it's very important that we look at other information that can give us some light about why this is happening. Because, it can be that one of the capillary pressure curve has a bimodal pore system, for instance. How do we know that? Well, of course, we look at the shape of the capillary pressure curve, but it will be very, very important, for instance, to look at thin section data. Right. And also, is there a fracture? Is there a fissure in one of the samples? Why do we start, as you say, why do we have a capillary pressure curve that starts very good, but then at the end crosses over with another, and the water saturation is higher? Maybe we need to see at the rock and see what if there is a variation in grain size from one sample to the other that is affecting the pore system and then affecting the mercury injection capillary curve. Because when they cross, we really sometimes the answer is I mean, you see that they cross and we don't have the answer really. But looking at the rock data, especially, I think that the best data to look at will be thin sections to see, that if there are different grain sizes or if there are fractures in one of the samples as related to the other that could be affecting the pore system and therefore affecting also the capillary pressure curve and causing this crossover.
Yeah, thank you very much. I appreciate that. And I think I'm taking the last question now from Chukwu Ebuka, University of Houston, United States of America. And he is asking, you used the mercury saturation quite a lot relative to capillary pressure. And I want to ask if you could use any other parameter apart from mercury saturation as a function to relate the measure of capillary pressure. Rather than using the mercury saturation, could you use any other parameter? That's the question he's asking. Chukwu Ebuka from University of Houston.
Okay, I'm not sure, but I will say a couple of things. The method that is used or that better works for rock typing is mercury injection capillary curve. Why? Because the pressure that is exerted to the sample can intrude or penetrate all the pore system in the rock, the good pore system and also the bad pore system, of course, right? There are also other methods, which are the centrifuge method or the restore state method that can be used, for instance, to determine the reducible water saturation, but they don't work very well for rock typing, to determine rock types. Also, we can use sets of relative permeability curve that are usually also, the shape of the relative permeability curve sets is related to rock quality. For instance, if we have a capillary pressure curve that is jumping from left to right and the irreducible or critical water saturation is increasing, that's usually what happens. You will have an increase in irreducible or critical water saturation as we have poor rock quality. But the best way to go will be use the capillary pressure data from mercury injection and then also integrate with relative permeability data. In fact, in this talk, I had some slides that represent the relation between mercury injection or capillary pressure curve and relative permeability, but for the sake of time, I had to exclude those. And then to summarize, we could use restore state and centrifuge, but we have an error. There will be uncertainty on the results because the one more appropriate for the rock typing methodology will be mercury injection. And also, if we don't have capillary pressure curve, and do have relative permeability curve, we can also relate that to rock quality. In fact, there is a very direct relation between all endpoints and crossover points in a relative permeability curve and some points in a capillary pressure curve.
Thank you very much.
But again, the best for rock typing, it will be mercury injection.
Right, thank you very much. I'm just to add a little one here because these are concerns that are raised. Hello, yeah, Carlos Vega is asking. He said there are certain times when you compare the R35 against SW's water saturation, and they correspond with each other. There is seeing the alignment, but at certain times they do not have that alignment. Do we say that the first case where we have the alignment corresponds to fluid, another case is driven by the lithology? Just briefly wrap up that before I conclude as the chairman of this forum, please. You understand my question, Carlos?
Not quite. Why sometimes there is not a direct relation between
why they correspond sometimes? Yes, the R3 corresponds with SW. At times it does not correspond with RSW. What are the factors that influence the alignment and non-alignment?
Okay,
is it has to do with the fluid or it has to do with the lithology?
Well, I would say that more important, because let's suppose this, when we talk about the water saturation and related to R, usually we're talking about, remember what I call minimum water saturation or irreducible. I don't like to call it irreducible, but sometimes we call it that way. Sometimes if there is not a relation, right, on the logs, one of it could be that the reservoir has been depleted. Okay, but sometimes that's what happens. The reservoir is depleted, so there is not a direct relation. For instance, the case that we looked at the same sample. Something that can happen also is more than lithology, but it's related to lithology, I would say, the dianetic processes that lithology has undergone.
Okay, that's fine. Okay. Thank you.
Yeah. Okay, well, you're welcome.
Yeah, thank you very much.
Please, I have a question.
Okay, what's your name, please?
Okay, my name is Okechukwu Agbasi. Jokan.
So sorry, and I would like to ask something for the last question. We have to see that when we have the water saturation based on the logs, also there might be some uncertainty introduced, especially by the resistivity logs, because if we are in irreducible water saturation conditions, the resistivity log should follow the rock type profile. If it doesn't follow the rock type profile, one of the reasons might be because we are not in irreducible water conditions. Just to close the question, the previous question.
All right, thank you. Dr. Okechukwu, what is your affiliation? Can we have your affiliation? Introduce yourself and then go straight to the question. We are running out of time, please.
Thank you. My name is Okechukwu Agbasi. I'm affiliated with Jokan Geophysical Services. My question is the capillary part of calculating or estimating the rock typing. How related is this with a Bock's plot method for rock typing? And it's actually very similar, but which of them would you recommend for rock typing? Do we go through the capillary method or do we use the Bock's plot method? Thank you.
The Bock's plot, well, so always we use both, always. But to say that I would recommend one, really, I wouldn't say. I have more confidence in the data from capillary pressure curve if we have a good set of capillary pressure curves that represent all the rock types in the reservoirs. Because the Bock's plot, usually when we construct a Bock's plot, we construct it from log data. And the logs are affected by many things. I mean, the logs are more affected, have many more factors affecting the resistive model than the factors that we have affecting capillary pressure. So I would prefer, let's put it that way, to use a capillary pressure analysis and then integrate with the Bock's plot and see how we can, do both and use both in the analysis. Because it's not a matter of doing one or the other. I think we should integrate all the information.
Thank you very much, Dr. Joan.
And sometimes the Bock's plot give us more information about storage capacity and the rock typing, more information about flow capacity and flow efficiency.
Thank you very much. I so much appreciate your work. This is a detailed job, but I want to take you, as the last bit before we round up here, I want to take you to the field. Last year, 2022, we drilled a well in southwest of the Niger Delta, south of the Niger Delta here. And we got to the pay zone as projected in the seismic, as was interpreted. And we got to the pay zone and discovered that the oil is there, but it's a tight reservoir. We couldn't produce. We have to suspend the well. Having looked at your presentation packages, we've seen that you've done some research work in certain part of the petroleum basins in the world, petroleum provinces. And you have also listened to your talk, and you have the non-conventional and conventional reservoirs. Is it possible that we could use this work to have a model? Could you go further to have a model that it could be used in some of the petroleum, like in Niger Delta, because you've not done, I've not seen a reflection of this part of the world, that is the Niger Delta, tertiary or even Cretaceous, that we could have a model that when you have a reservoir with this kind of lithology or behavior, the crude sample itself was not a heavy crude that one would say, let's go for enhanced recovery. And one could not, and we've not heard of any frac job like is in in Texas Basin, United States, where we have frac jobs. But in Niger Delta, I was surprised that we have a reservoir that there is oil we could not pull out. And the oil is not like a low API crude, like less than 20 API, and becoming a very heavy crude. And so we suspended the well. Could we have a model that if we key in some of the parameters of the reservoir and the oil, and we could have a model that we say, with this is the recovery method you could use. And with this range, this is the recovery method you could use. If it is in this country, if it is this basin, if it is a Chinese basin, if it's in the North Sea, if it's in a coral reef or whatever, this is the model of recovery, enhanced recovery. And since your background shows that you are a reservoir engineer and with a strong bias in geoscience, by experience, this model could help people all over the world, and it could help to showcase you, expand the work very well. And such that model would come to stay, and anybody can lay hand on it if he runs into such a problem. And if it is possible, I can really have an offline discussion with you and present, link you up with how we can get back to that well that we suspended and see whether we can make recovery.
Yeah,
that is my personal input. Thank you.
Yeah, no problem. You know, the big, I always say, like, when you do a rock typing model, there is a lot of added value that you obtain, because you can see, you know, even if we are in a conventional reservoir or a tight or non-conventional, you can see the better zones of the reservoirs. You can see the zones that might be with oil but are non-reservoir because they are very tight, very poor quality. And that the good thing, I always say this, you know, the methodology is very easy to use, honestly. Everybody can go ahead, take capillary pressure curve, determine rock types, and so on. But the important thing is how you apply this rock typing model to your case. You know, because it can give you an opportunity to have different decisions of having a conventional interpretation. For instance, where to test, where to perforate, where to inject, you know, things like that. Where is the free water level? You know, why is this zone having a higher water saturation than this other zone? Is this a matter of fluid, or is it a matter of rock quality? So I think, you know, always it's helpful to have a rock typing model, and then integrate with all the data, with the knowledge that the people have in their working area to make better decisions about a well or a field.
Thank you very much. Okay, thanks a lot, audience. I thank you for your time, and thank you, Dr. Joan. I have seen observation here that somebody is having question from Unical. Please channel your question through Dr. Harry, the coordinator of your Calabar chapter, and then possibly you could be made to talk to or have a chat through mail with the presenter, Dr. Joan. Dr. Joan, I want to appreciate you having given your time and resources to make this presentation to the chapter promoting NAPE. This is a very detailed work, and it's worthy of representing it in the international conference where we could have a wider forum and participation, because it has to do with producibility of the reservoir, proficiency of the reservoir. And generally, that is the problem a lot of operators have right now in the Niger Delta, practically, and not only Niger Delta, globally, because where you are really well, you got to the reservoir, you got to the pay zone, you cannot produce. And so many countries, some do not practice fracking, and because it's not shell, and just suspend the well of probably about $20 million. And you see how businesses are closed. So this is a topic that more justice should be done, more research should be done, model developed. And I believe that you have a long way to go with this. We highly appreciate you in the chapter. On behalf of this chapter, we say thank you so much. We cannot reward you for this excellent talk. We'll surely meet again, surely invite you again to give a talk that is this rich. Thank you very much.
Well, no, thank you. Thank you for the opportunity. And as a final message, I say that a rock typing model should be a routine should be a routine. Okay, yeah. As a final word, I would like to say that, you know, a rock typing model should become a routine work for any reservoir.
Yeah, thank you very much. Yeah. So at
Thank
this
you very
point, I hand
much,
over to
my chairman, and thank you very much, my presenter, Dr. Joanne. I want to recognize the presence of former President, Dr. Alex Tucker. We are welcome, sir. And if you're still here, sir, I would like to have a word with you on behalf of National NAPE. The president is in a function, he would have been here. They're actually in a conference right now, an international conference on oil and gas. So please, is the Dr. Tucker still on the board? I would like to have a word with you. I'd like you to have a word with us, please.
Dr. Taga, please unmute yourself. It's still being muted. Tunde should unmute him.
Okay, it's unmuted. Okay, all right. So maybe it's not available right away. All right. So to round off, would have continued this very interesting talk, but we have to go now because of time. I want to thank everyone for coming on board, and without much ado, I'd like to invite Dr. Chimezie Emeka to round off with the closing prayers. Thank you. General Secretary, Dr. Chimezie. Okay, if he's not here, please come. Professor Idara, say the closing prayers, please.
Okay, Father, we thank you once again because you have been with us throughout the presentation. We thank you for the grace that you have accorded Dr. Joan to upload this side of knowledge to us. We thank you for all the participants in this workshop, and we pray that the knowledge that has been brought to us will be able to use the knowledge and propagate it to the glory of God, and then in the oil industry, we're able to solve some major issues and challenges that we have faced. As we depart, oh Lord, we ask that your presence continues to be with us. Thank you, Lord, once again. In Jesus' name, we have prayed. Amen.
Amen.
Thank you very much,
Professor
and have
Idara.
a wonderful time. Thank you for participating. We'll have this presentation on the NAPE YouTube channel, so you can always go there to NAPE YouTube channel and then have a review of the presentation and also get the slides. Thank you, and God bless you.
Thank you.
Thank you so
very
much, my
much.
chairman.
Thank you very
Dr.
much
Harris.
again.
Yeah, thank you. Thank you, Joanne. Thank you, everyone.
Appreciate you guys. You guys are doing very well.
Thank you very much. I thank the ESCO
Thank you,
members.
Dr. Harris.
Prof, thank you very much. Carlos, thank you so much. Carlos Vargas,
We would have loved to see his face,
one
but
of
he did
our
not show
former
his face.
speakers. Interesting.
Yeah, thank you, everybody.
Thank you, Ogatunde. Thank you
You're
very
welcome.
much.
Thank you. Great job.
Great job, Ogatunde.
Yeah,
We're
well done.
national people now.
Well, they are at Abuja.
You saw it?
I said our people at Abuja. For the
Okay,
NIS
they're in
conference.
Abuja.
Yes.
Okay, for the conference.
Yes, the NIS conference. The president
Okay,
is there.
no wonder.
President
Thank you very
elect is
much.
there.
We had a wonderful time.
You too.
Thank you. I believe it will be available on the YouTube channel, right?
Yes, live.
All right.
I'll send
Thank
the
you.
link to you.
Thank you, my chairman. Oh, my chairman, you look so good.
Really?
Yeah, and it was such a wonderful job.
It was a good time. I really enjoyed it. I had to make myself available. I've learned so much. I will try and see how to
I
contact
can see
him.
Dr. Chris Jackson here. Dr. Chris, you're here on board?
Really? Is
Yeah,
he in?
I'm very much here.
Ah,
I'm here.
awesome.
Chief Chris.
Thank you so much,
I
sir.
salute you guys. Yeah, thank you. Thank you, Dr. Harry. You are doing a great job. And Dr.
Yeah.
Nkere, everybody,
Yes.
Prof. Fabio, and everyone. Thank you.
Thank you very much.
I thank the Exco so much.
Thank you for coming.
Your Calabar Expo has done so well.
Yes, thank you. All right, bye-bye. Have a nice time.
Bye-bye.